Hello and good afternoon, everyone. Welcome to SINP Theoretical Physics Seminar Series. Today we have among us Professor Govind Krishnaswami. Govind did his PhD from University of Rochester, and after postdoctoral positions at Utrecht and Durham, he joined Chennai Mathematical Institute, where he is presently a professor. Professor Govind is interested in various aspects of theoretical and mathematical physics. And today he will be talking on chaos in the three-rotor problem. So without further ado, I welcome Professor Govind to start his talk.
Thank you, Sabyasachi, for this very nice introduction, and also Devashish for the invitation. Very glad to be present at Saha Institute virtually to give this seminar. So this is, I was told to keep it broad so that the diverse audience of theoretical physicists from different areas can get something out of it. And please feel free to stop me when if you have any questions. So this is work that is based on these two papers mainly, published in Chaos. They were done with, this is work done with Himalaya Senapati, who just got his PhD recently. So this is the fun we've had over the last few years. Okay, so this is about the three-rotor problem. So please do stop me if my audio is not good or you can't see things clearly. I have some movies as well, so I hope things go well. So the three-rotor problem, or what we call the three-rotor problem, is one where three equally massive point particles, which we call rotors, move on a circle without collisions and interact via attractive cosine potentials. So this movie will tell us a typical motion. So you have the red, yellow, and blue rotors, they're going around. You notice that they can pass through each other without any singularity or collision. There are pairwise forces between each pair, which is the cosine of the difference in angles. Let us see where this problem came from. First, it's just the setup. So if we call the angular positions of the three rotors theta 1, theta 2, theta 3, so they are distinguishable objects. Then the configuration space is a three torus, product of three circles for each of the rotors. And the Lagrangian is very simple, half m r squared theta I dot squared minus a coupling times 1 minus cosine of the difference in angles between the ith rotor and the I plus first rotor. So you could, of course, consider this for n rotors, not just three. But here we will look at three, and in this notation, theta 4 is the same as theta 1. So they are in a chain, a closed chain. So m is the mass of each rotor. We will take all rotors to have equal masses, and r is the radius of the circle. These don't play any significant role, and we will largely put them equal to 1. G is the coupling constant. It is the strength of the interaction. Now, one reason to be interested in this system is that the quantum version of this system for n rotors models chains of coupled Josephson junctions. So this is explained in this paper by Shivaji Sondi, Steve Gerwin et al., where rotor angles, the thetas, correspond to superconducting phases of metallic segments. So you have a chain of Josephson junctions. These are the junctions. And then you have the metallic superconducting segments between junctions, between the tunnel junctions. And in each superconducting segment, you have a superconducting phase, which is associated with an angle. So those are the angles of our rotor system. Now, the Josephson junction, coupled Josephson junction energy in the quantum theory consists of a potential energy, which is the Josephson coupling energy across the tunnel junction, which goes as the cosine of the difference in superconducting phases. And then you've got a capacitive charging energy, half CV squared, which in the quantum theory is written in terms of derivative with respect to the rotor angle. So that is the kinetic energy in the rotor system, or the capacitive charging energy associated to the voltage in each of the metallic segments. So if one regards this as a classical version of the coupled Josephson system, then we come to understand why it's okay for rotors to pass through each other without collisions. And that's because rotors correspond to phases at distinct sides of the chain. So there is nothing wrong with θ1 being equal to θ2. Nothing special happens then. Of course, the force between them may take a particular value, but there is no collision. And it's completely physically accurate to think that way. And that's also why we can think of these rotors as distinguishable particles. They're not identical particles. I mean, they're identical but distinguishable particles. Because the phases at distinct sides of the chain are physically distinguishable. So this is one reason to be interested in this model, aside, of course, from being an interesting dynamical system in its own right. There are other reasons which are closely related. In statistical mechanics, you have the so-called XY model, where so the quantum n-rotor problem also arises from a partial continuum limit of the two-dimensional XY model of classical statistical mechanics. Now, in this model, we have a two-dimensional lattice, a square lattice or a rectangular lattice with planar spins, two-dimensional spins at all the vertices. And if you have capital N sides in the horizontal and M in the vertical direction, you have this rectangular grid. And if you request that you model the interactions as ferromagnetic nearest neighbor interactions, then the spin-spin interaction energy is just written in terms of the angle that these spins make with a reference direction becomes the cosine and difference of angles. Now, you do a little sleight of hand and convert the vertical direction into time. You do a kind of Wick rotation. And you take a continuum limit in the vertical direction while retaining a spacing A in the horizontal direction. Then this two-dimensional XY model through this partial continuum limit becomes the action of the quantum n-rotor model. So just a couple of facts about the XY model. So the XY model in statistical mechanics displays the famous Kostelis-Thouless topological phase transition. And it's associated with the unbinding of vortex-anti-vortex pairs as the temperature is increased beyond a Kostelis-Thouless temperature. So these vortices have to do with certain configurations of the spins sort of going round and round, either clockwise or counterclockwise. And the unbinding of these is associated to a transition. And at this transition in time temperature, the correlation functions are expected to transition from power law at low temperature to exponential decay at high temperature beyond the Kostelis-Thouless critical temperature. And field theoretically, this may be regarded as a transition from a massless or ungapped phase, massless phase with the power law decays of correlations, to a massive phase, gapped phase with exponential decay in correlations. So one of our original reasons to look at this model had nothing to do with rotors. We were just interested in understanding mass gaps in simpler models compared to Young's theory. So I thought the Nobel Prize to Kostelis-Thouless, a few years back. So we began looking at this model. But a lot of that is already known in the condensed matter literature. As we looked at this more, the system, the problem took a life of its own, and a new avataram was born. And that avataram is what I'm going to describe to you, the rotor system. But this motivation can be kept in the background. Now, there is more motivation as well. So the classical three-rotor problem may be viewed as a simpler variant of the gravitational three-body problem, the venerable gravitational three-body problem, the Sun-Moon-Earth problem, for instance. Now, as I said, the configuration space of this three-rotor system is just a product of circles this is a compact manifold, unlike the configuration space of the three-body problem in celestial mechanics, which is Euclidean space, R9. And moreover, the potential here, which we have taken to be the cosine of difference in angles, is a bounded potential, unlike the Newtonian 1/r potential. So in some ways, it is simpler. For instance, the rotors cannot escape to infinity. They're confined to circles, nor can the dynamics produce singularities. On the other hand, such singularities can arise in the gravitational n-body problem. So just in the spirit of giving some more cultural background, let me just mention something about singularities in the gravitational problem. So as you are aware, when two gravitating point masses approach and collide, their relative speed diverges and the solution becomes singular at the collision time. This is, of course, a well-known problem of classical mechanics. Now, more generally, we will say that a singularity occurs when either a position or a velocity diverges in finite time. That's important. It must diverge in finite time. Then we will say that the system has encountered a singularity. Now, for Pendulum in 1895, the French mathematical physicist showed that in the three-body celestial mechanics three-body problem, the only possible singularities are binary and triple collisions. I mean, these are the obvious possibilities where, I mean, the sun and the earth collide, or all three, sun, moon, earth, all collide at a certain time. And he showed that these are the only possibilities. However, he conjectured that certain non-collisional singularities can occur if you have more bodies, like 4 or 5, etc. And these are called non-collisional singularities, where without any collision, either a particle escapes from the system in finite time, or a velocity reaches infinity in finite time. So these are called non-collisional singularities. And it took nearly a century for this conjecture to be established, to be proven, culminating in the work of Donald Sari and Jihong Xia in the United States, as well as Joe Gerver in the United States. I think he's at Princeton. So they found explicit examples of non-collisional singularities in the 5-body problem. That was Xia Sari's work, and in the 3n-body problems for Joseph Gerver. So let me tell you an example of such a non-collisional singularity. It's a very nice physical system. So this is Xia's example. You have two sort of tight binaries, two masses in their own little Keplerian type orbit, another two masses in their own little Keplerian orbit, and then a fifth mass that oscillates between the two. I mean, this initial conditions can be chosen so that the equations of Newtonian mechanics actually produce such a system. So what happens if you choose the initial conditions suitably, the messenger mass oscillates with ever-growing frequency between the two tight binaries as the separation between the two binaries grows with time. Yeah, this is going back and forth. Each time the messenger approaches this pair, it extracts a little bit of their energy and the two get closer. But in the process, they get pushed away while this messenger recoils and comes towards the other binary pair. So as the time goes, the two tight binaries get further and further apart, and the messenger oscillates with ever-growing frequency and amplitude between the binaries. And in finite time, remarkably in finite time, the binaries escape to infinity, and the intermediary is going back and forth with a infinite velocity.
Hi, can I ask a naive question here?
Yes.
Yeah, okay, since you say that the separation between the binaries sort of diverge in finite time, it seems that if I just calculate the energy, it's just some kinetic energy in some finite time, and I can ignore the potential terms. But is that correct? Because this initial configuration seems, yeah.
No, there is a potential energy in each of the binary systems, and maybe I didn't emphasize enough, each binary is getting tighter and tighter. So each
I see.
energy is actually becoming more and more negative.
Okay.
Each energy is growing, and total 5-body energy is conserved.
Okay, thanks. Yeah.
Yeah. But that's a very good question, and it's possible that such a thing can actually be occur in the universe somewhere. Simpler versions of this do happen. Numerical experiments with rather simple initial conditions, like 3 bodies at the corners of a 3, 4, 5 Pythagorean triangle, start at rest, you just let it go. It turns out that as it evolves, one mass can fly off to infinity, but this is a 3-body problem. Here it doesn't happen in finite time, it takes infinitely long, but a body can fly off to infinity while the other 2 can form a bound system. So these were kind of precursors to that example. People played around with numerical experiments before finally discovering an example that proved Poincare conjecture. And this is probably even seen in so-called hypervelocity stars, where one star from a binary, so you have a galactic black hole and a binary pair, and so this is a 3-body system. One of the stars from the binary is sort of captured by the black hole, and the other is ejected at high speed. So many of these toy 3-body solutions, numerical and otherwise, may even be realized in nature. So this was my little background on non-collisional singularities in the n-body gravitational n-body problem. But we are now going to go back to the 3-rotor problem, where such pathologies, if you want to call them that, do not occur. On the other hand, because such crazy things don't happen, other aspects can be studied in depth, like the dynamics itself, the chaos and such things. So we will focus on those things. Yeah, so coming back to the classical 3-rotor problem, I remind you that we have 3 bodies on a circle subject to these cosine interparticle potentials, and that configuration space is simply the 3 torus. Now, okay, before the 3-rotor problem, you can consider 2-rotor problem. And the 2-rotor problem is just a simple pendulum, because you've got just the cosine of the difference in angles. So that is a solvable model. On the other hand, you can take a limit where the number of rotors goes to infinity, and this has been studied. And it is even described in Subi Sachdev's book, I think. And so that limit, I mean, a suitable continuum limit is described by the Sine-Gordon field. So the 2-rotor and infinite rotor problems are in some ways understood better. But between these extremes, we find that the 3-rotor problem and also 4-rotor, 5-rotor have rich dynamics and provide a non-trivial arena to study quasi-periodic solutions, instabilities, chaos, ergodic behavior, all these things. So that's what we're going to focus on now. Now, I just want to describe the setup that we use. This is the obvious possibility. We have 3 bodies. It is convenient to go to a center of mass frame. So we define a average angle, which is the center of mass variable phi naught, theta 1 plus theta 2 plus theta 3 by 3. Remember, the masses are all equal. Unequal masses are interesting as well, especially in gravitational physics. But we are keeping things simple here. And then we have the 2 relative angles, phi 1, which is the difference between the first 2 rotors, and phi 2 is the difference between angles of the second 2 rotors. Now, as you might expect, the relative angles phi 1 and phi 2 evolve independently of phi naught. These are the equations for those relative angles. There's a 1-2 symmetry, of course. And they're, of course, very nonlinear. I mean, if they were just sine phi 1, this would be like a pendulum, but there's also the coupling between the 2 rotor angles. So this is a highly nonlinear dynamical system. Now, the 2 relative angles, each is takes values between 0 and 2 pi. So you've got an effective configuration space for the motion sans the center of mass motion, described by a torus, a 2 torus, phi 1 and phi 2. And the system is Hamiltonian. There's a potential. And I have plotted the level curves of the potential here, level contours. So the relative energy in units of the coupling constant is the only known conserved quantity. So you have 2 degrees of freedom, a 4-dimensional phase space, and just one conserved quantity, namely the energy in units of the coupling constant. And you can think of E in units of G as a control parameter, dimensionless control parameter, and we are going to see what happens to the system as we vary this energy. So here is the energy. It consists of the kinetic energy, phi1 dot squared, phi2 dot squared, but also a sort of a cross term, phi1 dot, phi2 dot, as well as certain cosines of relative angles, and also the phi1 plus phi2. So this is the energy of the system. It is, I mean, of course, you are tempted to perhaps consider diagonalizing the kinetic energy to go by going to so-called Jacobi variables like phi1 plus phi2. But you can't really separate them because then the potential energy will also get mixed up. So we will continue to work with these variables for now. Now, as you might suspect, the system at very low energies is integrable. In fact, the ground state is, and now I'm going to ignore the center of mass motion. The center of mass motion is very simple. The whole thing simply rotates. So we will focus on the relative motion. For the relative motion, the ground state is the static solution at the global minimum of the potential corresponding to all 3 rotors being aligned, all 3 rotors aligned. So this is the so-called ferromagnetic ground state of the system, all rotors aligned. There are 2 other types of static solutions at energy 4G and 4.5G. They occur at a saddle points of the potential energy and at maximum of the potential energy. So those are called D and T. So the static solution at D is kind of a diagonal state. It's a kind of anti-ferromagnetic ground state where you have rotors, one rotor at one end of a circle, at one point of the circle, the other 2 at the opposite end, diametrically opposite end, so that it's like up, down, up, nail kind of state. And then finally, you've got a maximum of the potential where the 3 rotors are equally separated in angle around the circle. So this covers the static solutions of the relative motion system. So as I was saying, at low energies, we have small oscillations around the ground state, and you have 2 conserved normal mode energies. So the system becomes integrable, 2 degrees of freedom, 2 conserved energies, normal mode energies. On the other hand, when the energy is very large compared to the coupling constant, the kinetic energy dominates. And in this limit, both the rotor relative angles become cyclic and the rotors rotate uniformly around the circle. So these 2 limits are very much under control, but we will see that interesting things happen in between 0 and infinite energy. Very interesting things happen. And our first window into these phenomena will be through periodic orbits. So just as a thought process, we before working on this 3-rotor problem, Himalaya, Senapati, and myself, we were looking at the 3-body problem, the planar 3-body problem, gravitational one, as well as 1/r² potential. So one reason we came to this problem, we wanted a simpler problem compared to the 3-body problem, but it's still quite difficult in some ways. But we followed whatever historically was done in the gravitational 3-body problem. We tried to replicate here, and some of the earliest results in the gravitational 3-body problem concern periodic solutions, and these are associated to the names of Euler and Lagrange. So just let me recall some of that for you. The most famous solutions of the 3-body problem are those of Euler and Lagrange, where the 3 masses traverse. They need not be equal masses. Sun, Moon, Earth will do just as well. 3 masses traverse Keplerian orbits. Each of them traverses a Keplerian ellipse in the simplest. And in Euler solutions, the 3 masses remain collinear. So here's an example. The 3 remain collinear, and that axis simply rotates. Collinear with constant ratios of separations. So you can have slightly more interesting ones where each of them traverses an ellipse, but the line joining the 3, but there is always a line joining the 3, a straight line joining the 3. So these are called the Euler solutions. They're periodic solutions. And then you have Lagrange's solutions, which are slightly different. where the three bodies always lie at vertices of an equilateral triangle. So here you have an example. Each of the masses traverses a Keplerian ellipse. But the bodies as a whole lie at vertices of an equilateral triangle. The triangle itself can grow in size and decrease in size, as you can imagine. So we plotted this triangle at different instants of time. So these are some fun solutions of the gravitational three-body problem. More recently, there are other solutions to the three-body problem that have been found. Now, in the times of the Olympics, choreographies will sound nice, perhaps. So choreographies are periodic solutions, even for the n-body problem, where n equal masses follow each other at regular intervals in time around a closed path. So, I mean, the very fact that such solutions exist is in some ways a surprise. And they are sometimes found by numerical methods and also by variational methods. So let me show you a picture of such a movie of such a solution.
So quick question. So this n can be quite large as well, or I mean, in this choreographic solutions that you mentioned?
The choreographies I'm showing are when, there is no restriction on the mass of the particles.
No, I mean n, the number of such particles.
No, of course, different types of, for each n, there are several classes of choreography. So I'm going to show you n equal to 21 in the next picture.
I see. Okay.
So no, there is no restriction on the number of particles. I believe there are choreographies. In fact, there is a whole atlas of such choreographies.
Okay, I see.
Very interesting pictures. And there are a lot like synchronized swimmers that we will see in Tokyo. So let me show you one such. And the path traversed by the 21 bodies is this funny curve. And they're all equally separated in time, not in distance. So here they go. This is an actual solution of Newton's equations subject to 1/r potential attractive. And so you see what a choreography can look like. But they are not restricted to by the number of particles. And there is a small industry of finding such solutions. I mean, the most famous choreography in recent times is the figure-8 solution, which kind of started out a lot of the work that has been going on the last couple of decades. You have three bodies that follow each other along an infinity-shaped path. And this was discovered numerically and also proved to exist analytically. There's a nice literature on that as well, and the figure-8 solution of the three-body problem. You can look that up if you're interested. So what we found are that we have found analogues of the Euler and Lagrange solutions, as well as choreographies in the three-rotor problem. So let me show you some of them. In fact, we find families of periodic solutions. I mean, families means parameterized by energy. So we call them pendula and breathers. They exist at all energies, and choreographies exist up to moderate energies. We can prove this. Now, in pendula, two rotors form a bound pair with zero separation, like a little molecule, and the third rotor is somewhere else. And the equations for this system reduced to that of a pendulum, ordinary pendulum. So that's why we call them pendula. But of course, they're embedded inside this three-rotor system, just like the three-body solutions of Euler and Lagrange are really Keplerian solutions embedded within the three-body problem. So it's somewhat similar in spirit. Let me show you a picture of a librational pendulum solution. So you've got a molecule. The blue one is a molecule consisting of two rotors, and then the yellow one is the third rotor, and they're sort of oscillating merrily. So this is called a librational solution. You've got also, they exist as long as the energy is less than 4G. And for energies more than 4G, you've got rotational versions where they can kind of go around the circle. As you can imagine, a pendulum can oscillate this way, libration, or go all the way around. So that's the analog. So these are rather simple periodic solutions, but the remarkable thing is that these periodic solutions can, in a very intricate manner, encode deep information about chaotic dynamics. And this idea goes back to Poincare to study periodic solutions in depth. So those were the pendulum type solutions, and then we have also these breathers or isosceles solutions where one rotor is always exactly between the other two. So this is another class of periodic solutions. We've got choreographies as well. They're not as dramatic as the synchronized swimmers, but I'll quickly show you one such choreography. If you follow closely, the time the red one takes to reach the North Pole is exactly 1/3 of the period. After 1/3 of that period time, the yellow one will reach, and then another 1/3, the blue one will reach. So one can follow this closely and discover that it's actually a choreography. Yeah, but our focus will mainly be on these so-called pendulum solutions, and they display remarkable stability properties. So let us see what that is. So here is, so we went ahead and studied the stability of course, even in the gravitational three-body problem, people studied the stability of the Lagrange points, for instance, as a function of the masses of the bodies. So there's a literature on that. So here we are looking at the stability of these pendulum solutions. Now, how do you study the stability of a solution? Well, of a periodic solution, there's a simple idea. You have a periodic solution here. I've displayed it as a circle in phase space, a periodic solution called psi naught. Then you consider a small perturbation, a tangent vector at the initial location, and a perturbed trajectory. Now, that perturbed trajectory is going to return to some point somewhere and define a new tangent vector after one period of the base solution. Now, and that defines a linear map in the tangent space at this point for perturbations. And the perturbation after one period of the original solution is related to the final state through a matrix, linear transformation called the monodromy matrix. So now stability concerns what happens to the perturbation after a long time. So in particular, suppose you wait for several periods of the original periodic solution. And that will be governed by composing the monodromy matrix with itself several times. So after n times the period of the unperturbed solution, you'll get the nth power of the monodromy matrix. So you can now see that the stability of this solution, the delta psi, the stability of the original solution, periodic solution, is determined by the spectrum of M. So if the eigenvalues of M are more than 1 in magnitude, then the perturbation will grow. If they are less than 1 in magnitude, the perturbation will decay. And in this manner, one can examine the stability of a periodic solution. So if you do this for the pendulum solution, to make a long story short, as I said, the stability is determined by the eigenvalues of the monodromy matrix. And in this case, it can be encoded in the trace of the monodromy matrix. In fact, there's something called the stability index, which is the difference between the trace of the monodromy matrix and 2. Now, if that stability index exceeds 1 in magnitude, exceeds 2 in magnitude, then the original periodic solution is unstable. And if it is between between -2 and 2, then the original periodic solution was stable. Now, we do all of this for our pendulum solutions as a function of energy. Remember, we have a family of solutions parameterized by energy, a family of periodic solutions. And for each energy, we ask whether this pendulum solution is stable or not. What do we find? We find that at very, very high energies, so this is a logarithmic scale, at very high energies, pendula are stable because the stability index is bounded between -2 and 2. But as the energy decreases, there's a critical energy, E1R, at which the pendulum becomes unstable. It remains unstable for a certain window of energies, and then again becomes stable. Now this is repeated. This pattern is repeated. And this is a logarithmic scale. We find that it is repeated asymptotically, periodically on a log scale from high energies and similarly from low energies. So in other words, at very low energies, low energy pendula are stable. And then there is a critical energy at which the pendulum solution becomes unstable. It remains unstable for a certain window of energies, then again becomes stable, then again unstable, again stable. Now these windows become shorter and shorter because it's a log scale. And what we've discovered is an accumulation of stability transition. In this log scale, it's periodic, but in the true energy scale, it is then geometric. So there's a geometric accumulation of stability transitions. There's an infinite number of doubly infinite sequence of stability transitions that accumulate at energy 4 in units where G is 1. So remember, G equal to, energy 4 is the transition energy between liberational and rotational pendula. So at that energy, it turns out that there is an accumulation of stability transitions. So this is quite a remarkable phenomenon, but there are precedents to this. Let me mention a few, though not directly related, but there are some precedents. So now this geometric accumulation of stability transitions bears a resemblance to the Efimov effect, again from three-body problem. I will just tell you what that is. It also bears a resemblance to stability transition in Yoshida's work on the two-dimensional anharmonic oscillator, as well as to the cascade of period doubling bifurcations in the logistic map. So just very briefly, what are these things? Yeah, so let me first talk about the Efimov effect very briefly. So in 1970, Efimov studied the quantum spectrum of three particles. So these, in his study, these were nucleons or alpha particles subject to attractive interactions. And he studied this in the limit where the S-wave scattering length, the k to 0 limit of the scattering amplitude, is much larger than the interaction range. So in his quantum mechanics study of this problem, he found the spectrum of such trimers, these three-body bound states. He found a spectrum of three-body bound states, and that he found that the spectrum forms a geometric sequence accumulating at the zero energy threshold, corresponding to arbitrarily weak two-body bound states with this diverging scattering length. So that's a mouthful, but if you, so for those who are interested, I invite you to go look up Efimov's work. But we have some kind of classical analog of that phenomenon. So the accumulation of these quantum spectrum at this threshold is a little bit like our geometric accumulation of stability transitions at the threshold for liberation to rotation transition in the pendulum system. And in a sense, the divergence of the scattering length that he was considering is a little bit like the diverging time period of pendula at energy 4. So you will remember that a pendulum has a finite period. As you increase its amplitude, the period increases, as given by some complete elliptic integral. And as it reaches the top, the period goes to infinity. So that's a little bit like this diverging scattering length. We don't have a precise connection between these two systems, but there are a lot of circumstantial similarities. So they're both three-body systems, completely different. One is quantum, others classical. But it's interesting that these geometric accumulations occur in both. So this is one similar phenomenon that has been observed. Another example, which is somewhat simpler, is a rather simple system. You take an anharmonic oscillator with 2 degrees of freedom, P1 squared, P2 squared, Q1 to the 4th, Q2 to the 4th, and an interaction term, alpha Q1 squared, Q2 squared. So this system, where alpha is the coupling constant, this system was studied by Yoshida, 1984. And what he found, okay, just like we have done, he studied a family of periodic orbits, some special solutions, periodic solutions to this two-dimensional oscillator. And he found a sequence of stability transitions at certain values of alpha as alpha goes to infinity. So in our system, we have found a doubly infinite sequence. He found a singly infinite sequence as the coupling constant went to infinity. So ours is again similar to this effect. So this seems to be a feature in many simple dynamical systems, simple in the sense of easy to write down. it also reminds one of the cascade of period doubling bifurcations in the logistic map studied by Feigenbaum. So you may recall that the logistic map xi plus 1 is equal to r times xi times 1 minus xi that we often study as a simple model for a discrete time dynamical system displays a sequence of period doubling bifurcations. So there's these are the attractors for the system. So there's a period 1 fixed point, and then there's a period 2 attractor, and then a period 4 attractor, and so on. And you have a sequence of values of the coupling constant at which these transitions occur. And what Feigenbaum showed and discovered is that this sequence of bifurcation windows, the lengths of these windows is geometric, approaches a geometric sequence with a common ratio given by Feigenbaum's constant. And he, an absolutely beautiful work, he found a way to find this constant using renormalization group methods as the eigenvalue of some linearized RG map. So this again is reminiscent of our geometric cascade of stability transitions, though we don't have any deep understanding about how all of these are related or how to use these methods over there. Okay, so this is a little bit of background for you. So, so coming back to our three-rotor system, coming back to our three-rotor system, we will see that this cascade of transitions so it is not just a cascade of transitions, it is also related to a rather sharp transition to chaos at energy 4G. All right, so.
So quick question. So when you say that the transition is at energy 4G, you mean, sort of above, sorry, not above, below that energies, all trajectories are, all nearby trajectories are chaotic, whereas above it, some of the trajectories may be non-chaotic. Is that what you mean?
Okay, this is going to be answered in one slide, I think. So when I say, okay, there are many transitions happening here. So to get ahead of myself, I'm going to show you that there is a transition to chaos over here. I have not described that yet, it's coming up. And perhaps that is what you're talking about. So I will describe in what sense that's a transition to chaos. And that happens to coincide with this accumulation of stability transitions. So that is a separate matter. The stability transition energies are this sequence of energies. They accumulate at energy 4, both from above and below. There's no chaos there. There's just some accumulation, some instabilities. But when that happens, coincidentally, there is a transition to chaos. Now, what do I mean by a transition to chaos? I need to make that precise, and I will do that in a moment. If it's just 2 slides away. So I will do it in 2 steps. So chaos has to do with instabilities. I think you will all agree with me. So we wanted to look at instabilities in this system in a novel way, and that is what I will describe on this slide. So this is so-called geodesic instabilities in this system. So what is that? Okay, so the onset of widespread chaos around 4G, which I'm going to describe in a moment, is associated with an appearance of geodesic instabilities in this system. Now, let me explain that in 2 sentences. It turns out that trajectories of the three-rotor problem can be viewed as reparametrized geodesics of a certain metric. This is due to Jacobi and Maupertuis. So this is a metric on the configuration space of the system. Here the configuration is a torus. So it's possible to describe a metric, define a metric on this torus. So that metric is given here. It's a very simple idea. You take your Lagrangian of mij phi I dot phi j dot minus v. So this is simply a quadratic Lagrangian, quadratic kinetic energy, some potential. You can define a metric which is conformal to the mass metric. So this is just the kinetic metric. And here you rescale that by the energy minus the potential. So this is a family of metrics, one for each energy. So for each energy, you've got a portion of the configuration space where the dynamics can take place. As the energy grows, you can explore more of the configuration space. And on each of those restricted portions of the configuration space, you got a metric. You can consider the geodesics of that metric. It turns out the geodesics of that metric coincide with the Newtonian trajectories just that you need to reparameterize time. The affine parameter for this metric is not the same as Newtonian time. You have to make a small change. But you can then study the stability of those geodesics by computing the curvature of this metric. And what we find very remarkably is that when the energy is less than 4G, which is the same energy at which the stability transition are accumulated, when the energy is less than 4G, this curvature is everywhere positive on the configuration space. It's not a constant curvature metric, it's a variable curvature, but it is positive everywhere. And positive curvature means that nearby geodesics oscillate around each other, stable. On the other hand, when energy exceeds 4G, the curvature of this metric can take either sign in different places on the configuration space, both positive and negative. So there is negative curvature would mean that nearby geodesics exponentially deviate, and you have geodesic instabilities. So we have another beautiful coincidence that at the same energy at which these pendulum instability transitions accumulated is also the point at which geodesic instability is set in our system. Now to come to chaos, perhaps the simplest way to see chaos is to study Poincare sections. So let me just quickly remind you what a Poincare section is. So you take our 4-dimensional phase space, put energy constant that defines a 3-dimensional submanifold, 3-dimensional energy hypersurface. Within that 3-dimensional energy hypersurface, which is rather difficult to visualize, you consider a 2-dimensional surface, which is called a Poincare surface S. Now you start a trajectory on S, you let it go numerically, and ask when it returns and intersects that surface. That is called the Poincare first return map. Q1 maps to Q2, and you continue this. Q2 will come to Q3, and so on. So, and you record all those points at which the trajectory intersects the surface, and you get a scatter plot. And this scatter plot is called the Poincare section for that trajectory. Now, if the trajectory were periodic, you can imagine that the scatter plot will just be a finite number of points, maybe just 2. I mean, just a circle cutting the surface, you'll just get 2 points. I mean, it's slightly more complicated, you may get 4 points and so on. In any case, Poincare sections allow you at a glance to identify the nature of the motion. So if the Poincare section is just a finite number of points, then the periodic motion is what's going on. If the Poincare section is concentrated on a 1-dimensional curve, then the original trajectory usually is quasi-periodic. That is, if the trajectory is not periodic, but confined, say, to a torus, quasi-periodic on a torus with 2 different periods, then if you go and cut it with a surface, it will intersect it on a pair of circles, right? Topologically at least. So if a Poincare section looks like a closed curve, then you say that the motion is quasi-periodic, and both of these are regular. On the other hand, a chaotic trajectory sort of wanders unpredictably all over the place. The Poincare section is not confined to a finite set of points or a curve, but explores a 2-dimensional region of that Poincare surface. So that is when we say the motion is chaotic. So let me go back and tell you what happens in our 3-rotor system. So in 3 rotors, what we find is that at low energies, here energy 2, we plotted a bunch of Poincare sections for various initial conditions. You will notice that all the Poincare sections are concentrated along curves, and we say that the motion is largely regular. There are also some periodic solutions. The C stands for choreographies. They cut it at these 2 points. Pendula cut it at those 2 points. Those isosceles periodic solutions cut it at these 3 points. Yeah, so you've got periodic solutions as well. Now, as the energy approaches 4, here 3.9, you notice that some scatter is seen. Some sections start occupying 2-dimensional regions, and that's when we say chaos is setting in. So it's not as though chaos only sets in at 4. There is a little bit of chaos below 4 as well, energy 4. And it sets in at in the neighborhood of the unstable fixed point. These isosceles solutions, it turns out unstable, and they are saddle points, and it sets in over there. And as the energy increases 4.1, the region of chaotic region grows quite rapidly. On the other hand, if you make the energy much larger, like 18, the Poincare sections again start getting concentrated along 1-dimensional curves, and the chaotic part gets much reduced. Yeah. these are our observations.
Sorry, a quick question.
Yes.
So what happens at 4? Is anything special happening, or I should just imagine something between 3.9
yes.
and 4.1?
So lots of things are happening at 4.
Uh.
But as far as yeah, so I mean, okay, the picture at 4 and 3.9 and 4.1 are not very different. So it is sort of continuously interpolating between these two. If that was your question.
Yeah, that was the thing.
Yeah, if that was your question, there is nothing particularly special at 4. No. Yeah, but there's another way to quantify what's happening, and that will, and then you will see that something is happening at 4. Okay, just in passing, let me mention that like in particle physics and kind of matter physics, as this chaos is setting in, certain spontaneous symmetry breaking also happens. So chaotic sections first appear around 4, accompanied by a spontaneous breaking of certain discrete symmetries that are present in this at low energies. I mean, they're present in Hamiltonian, but manifest at low energies. That is, if you have a trajectory here, it will be mirrored by another trajectory there, or the trajectory itself will be left-right symmetric and up-down symmetric. On the other hand, if one looks closely, one finds that, I'm very sorry, at low energies, every orbit is left-right and up-down symmetric. Whereas as energy grows beyond 4, not every orbit displays that symmetry. You may have a trajectory over here, which does not go down here. Yeah, so this is a breaking of the up-down symmetry, a spontaneous breaking. Or you may have a trajectory on the right, which is not, which does not explore the left lobe at all. So, I mean, the onset of chaos is also associated with certain symmetry breaking. Now, so to quantify this onset of chaos, we compute the fraction of the phase space, in particular, more precisely, the fraction of the area of this Poincare surface that is occupied by chaotic trajectories. So here, that fraction will be relatively small. It's growing. Can I
ask a quick question here about this fraction of chaos, because I'm slightly confused. So, of course, as you said, that when G is very small and when G is very large, the problem is integrable, right? So if I think of the Km theorem for like a small number of particles or like a finite phase space, I mean, naively, I would imagine that if I then increase G from either direction, like move away from those integrable points, of course, the thing doesn't become immediately chaotic. There are regions of chaos and regions of regular motion. And that's what you're also seeing, right? So, I mean, so where is the sharp transition to chaos? I mean, that's what I'm confused of, because this sounds just like a Km theorem, right? So,
yeah, you're quite right. We did say that at low energies, okay, just for convenience here, we are keeping G fixed. Maybe 1, and scanning over energies for definiteness. So for low energies, you're integrable, very high energies, again integrable. And you're quite right that Km suggests that as you move away from integrability, though there are no conserved quantities, there are no additional conserved quantities beyond energy, there are invariant surfaces, invariant tori that foliate the phase space, which slowly dissolve, and the chaos sort of sets in gradually. Now, yes. Now, I'm not saying that it is okay. This is slightly different from Km expectations, you might say, where the onset is somewhat more dramatic. But it is not that it is. You see, here it is 3.9. You do have. By the way, even at energy 2, if you look with a microscope around this point, you will find a little bit of chaos.
Yes.
So in that sense, it is not quite against Km expectations.
I mean, naively, it seems to me that this is sort of a crossover between two integrable endpoints, right? So is that correct?
Yes. Yeah, this is a kind of chaos order crossover or transition. We haven't looked at, Km perturbation theory in this system to, I mean, you would have to look at it more carefully to tell how quickly the tori are dissolving. We have not done such a deeper study, but yeah, if one had the idea that this would be more gradual, what we are finding is that it is somewhat quicker. Yeah, you might call it a crossover. And in fact, this fraction of chaos is quantifying that to some extent.
Yes.
You will see that up to energy 4, and in this inset, the fraction of chaos is basically 0, and then starts increasing at 3.8. So so it's not that something dramatic happens only at 4. There is a window over which the growth happens, but that window is relatively small. As you can see from this picture, the fraction of chaos is growing very rapidly, and then it drops somewhat more gradually. But you're right, we don't have any deeper understanding about why it is happening so quickly, and we definitely would like to have that. We only have certain other phenomena that point to energy 4. I talked about this accumulation of stability transitions, the onset of geodesic instabilities, and these spontaneous symmetry breaking. There's even another one. It turns out that the topology of the Hill region of configuration space, by that I mean the part of the configuration space that at any energy the system can explore. So that is some submanifold of the configuration space. That manifold also varies with energy. It turns out the topology of that manifold changes at energy 4. The topology changes, and that has some connection to these things, I'm sure. We don't have a dynamical understanding as to how those things are linked. Okay, so I think I don't have that much time, so I will only give an indication of what other things we find. Unexpectedly, from this figure, we find that the fraction of chaos hits 1. So if you look at this inset, between energy 5.33 and energy 5.6, the fraction of chaos is 1. In other words, if you look at these Poincare surfaces, practically the whole surface is occupied by a chaotic trajectory. There are, of course, periodic trajectories that survive at any energy. And if we are to, the expectations from chaos is that there is, in a chaotic system, there should be infinitely many periodic solutions, even in a regime of chaos, which may even be dense, but that still doesn't prevent a global chaotic regime. And that's what we find as the energy reaches 5.33, all the periodic, the quasi-periodic solutions shrink, and you are left with a regime of global chaos. So this suggested to us that at least in this window of energies, this system may display ergodic behavior, mixing and these kinds of phenomena. And so the rest of our work, which I will just indicate, was to study whether the system is ergodic in this band of energies. And that, of course, you need two things. Roughly you need to show that time averages and ensemble averages agree. And of course, they must agree with respect to some measure. You have to compute averages with respect to some measure. Here we use the usual Liouville measure, dp/dq wedge product. So to make a long story short, we are able to show that in this band of global chaos, the system displays ergodic behavior, and we are able to estimate how fast these time averages approach the ensemble average. It is a power law, 1 by root t. There's a power law which we are able to establish. So the history of ergodicity is quite long, goes back to Boltzmann, and that is the basis of statistical mechanics. But there were various attempts to get additional conditions which will ensure that a system behaves ergodically, stronger conditions. So the next was Gibbs, who looked at mixing, where you put some ink in a pot of water and let it stir, and it would mix. So, so one can define mixing more precisely, but we're able to show that our system, numerically, we're able to show that in this band of energies, it displays mixing as well. So that's a stronger condition than ergodicity. So we have a globally chaotic system that is mixing as well. So, okay, I'm not going to go through all these things, because I think I am practically out of time. Perhaps I will just show you one picture or a movie to display how this system is mixing. So this is the energy hypersurface at an energy that lies within this band of global chaos. We've used some coordinates in this three-dimensional energy hypersurface, which depicted it as a cuboid. Then we take a small set of initial conditions in a little volume. That's like my ink. And then we let it go. We let time evolve. And then you will see that those trajectories will spread out uniformly as time evolves. I mean, this box has periodic boundary conditions, and they will asymptotically get uniformly distributed with respect to the Liouville measure in the energy hypersurface. So this is a picture showing mixing in the system. So in the ergodic hierarchy, you've got ergodic behavior, which is the weakest condition, and also physically the most important condition. And you've got stronger conditions like weak mixing and strong mixing, and Kolmogorov and Bernoulli. So we are able to show that at least to some reasonable accuracy, this does display mixing. Yeah. So just to conclude, let me just mention, summarize some of the things. So we have viewed the three-rotor problem as a place to discover new phenomena and study aspects of chaos. So I described our trajectory through physics reaching this problem. It passed through the XY model and Josephson junctions and the gravitational three-body problem. But then we found this as a very interesting problem in its own right. We are also looking at quantum versions as well. So the problem is somewhat simpler than the gravitational three-body problem due to the absence of collisional and non-collisional singularities. So, I mean, even if you didn't hear anything else I said, please take away these non-collisional singularities of Pendulum. Pendulum is a very interesting character. Among other things, he became the Prime Minister of France. So by contrast with the astronomical three-body problem, even the quantum three-rotor problem is of interest. It models change of coupled Josephson junctions. So we are looking at the quantum version, spectral statistics of the energy spectrum. So we found analogues of the Euler and Lagrange periodic solutions and choreographies in this three-rotor system. And we discovered a rather sharp transition to chaos at energy 4G with several remarkable features. A sharp rise in the chaotic portion of Poincare surfaces, a spontaneous symmetry breaking on Poincare surfaces, an accumulation of stability transitions in pendula. I mean, if you've seen this anywhere else, please do tell me. I'd like to add more examples. And a change in the sign of the Jacobi-Maupertuis curvature on the configuration space. I mean, there have been many attempts to relate geometric instabilities to chaos. And I'm not sure that any of those examples have really been able to get a smoking gun kind of connection. I do believe that in our system, there's a very close connection between geodesic instabilities and the onset of chaos. And as I mentioned, also a change in topology of the Hill region of the configuration space that is also somehow connected to chaos, the onset of chaos in our system. So just above the transition to chaos, we find a band of global chaos, and we provide evidence for ergodicity and mixing in this band by showing that the Liouville measure ensemble averaged distribution functions of relative angles and angular momenta. So these distribution functions are found to agree with the corresponding distributions along chaotic trajectories, so indicating ergodic behavior. The phase space distributions of momenta show interesting phase transitions from Wigner semicircular distribution to bimodal distributions. We don't quite understand that. We also showed that trajectories emanating from a small volume, that movie, become uniformly distributed over the energy hypersurface, indicating that the mixing is, the dynamics is mixing. Finally, we've also looked at another aspect, namely the distribution of recurrence times to finite size cells, how long it takes for a trajectory to return to a given finite size cell in the phase space or energy hypersurface. And the distribution of those recurrence times follows a nice exponential law, and the mean recurrence time satisfies a scaling law with a very interesting exponent, which is consistent with global chaos. So these are some of the things we have had fun with. So just a couple of points of discussion. by contrast with, there are other systems where people have studied ergodic behavior, like Sinai billiards, where you have a stadium and excluded region and specular reflections of a body, or kicked rotors, a pendulum that is kicked every so often, periodically. So unlike those, three-rotor system furnishes an example of, at least conjecturally, ergodicity in a continuous time autonomous Hamiltonian system without boundaries or specular reflections. In the three-rotor system, we find a close connection between the transition to chaos and the onset of geodesic instabilities. And it could provide an example of ergodic behavior in geodesic flow on a torus of non-constant curvature. So just to give you an idea, one of the canonical examples of ergodic behavior is geodesic motion on a Riemann surface of higher genus. Yeah, I mean a double torus or triple torus, a constant curvature Riemann surface, constant negative curvature. You have one can prove, and Sinai has done that. Ergodic behavior. So our system is a torus, but the curvature is not constant, both positive and negative, and that somehow is able to bring chaos into the picture, and as well as ergodic behavior, at least for certain energies. And unlike in Yoshida's anharmonic oscillator, I mean, remember in the anharmonic oscillator that I described, there was a sequence of stability transitions, but he also found that there were certain coupling constant values or energies where the system was integrable, not just at 0 and infinity. Whereas in our system, we conjecture that there are no non-trivial energy hypersurfaces in phase space where all trajectories are periodic or quasi-periodic. That is, there are no integrable points between 0 and infinity in energy. It's only 0 and infinity. This is our conjecture. Now, we would, of course, like to understand the physical mechanisms underlying the onset of chaos in some more very simple mechanical way, nowhere near that, as well as its quantum manifestations, as well as extensions to more rotors. So, so thank you for listening. These are some more references. Yeah, I'm happy to take questions if there are any more.
Yeah, thanks a lot, Govind, for the very nice talk. Yeah, questions, comments.
Yeah, so can I ask a quick question? So, yeah, thanks for this very nice talk. So